Hi everyone, this is just a quick video on the physics of lightning. So lightning occurs because there is charge separation within the cloud. And so you get some regions where there's positive charge and some regions where there's negative charge. And when that charge builds up, you get a big enough electric field that then the charge can sort of create a spark and travel within the air. Now, most of the lightning isn't from the cloud to the ground. Most of it is from one cloud to another cloud or within the same cloud. Um, but in terms of the physics of lightning, there's still some things we don't quite understand. And so, for example, we're only really sort of beginning to understand where this charge even comes from, how the electric fields that we measure in the cloud are not sufficient enough to cause sparks, to cause lightning. Now, what we think is happening with the charge is that larger pieces of ice are colliding with smaller pieces of ice, and the larger pieces of ice are falling through the cloud and making the bottom of the cloud more negative, and the smaller pieces are being buffeted around in the air, and for some reason they seem to give off the negative charge. These are positively charged, and they sort of make the top of the cloud more positive. Exactly why the larger pieces of ice would become negative, I'm not entirely sure if anyone completely understands that. Also, why exactly we get lightning in volcanoes or on Venus, where obviously there is no ice. Um, Presumably it's static electricity, so there's some triboelectric effect, some rubbing things together to generate that static electricity. But no one really understands exactly what's going on there. Another issue is that we know exactly what electric field is required to generate a spark, and the electric fields inside a thunderstorm just aren't large enough. Now, there's been a number of theories that are being put forward. There's two main theories at the moment. The first is the runaway electron effect, and the idea behind this is that cosmic rays, sort of particles from space, they're coming in and they're hitting molecules in the atmosphere, and those molecules then give off electrons, and within the electric fields, those electrons are accelerated into other molecules which give off other electrons, and so on and so forth. And you get this avalanche effect, which is just enough that once it gets running, you can create the spark at electric fields that are less than what you would normally require. The second idea is that maybe around the large pieces of ice, there's somehow a spark of positive charge that forms, and that initiates the lightning strike in some way. Um, I, the last time I was looking at some papers, they were saying maybe both of them happen in lightning. But no one really knows for sure. These are just theories at the moment. Now, in terms of how lightning can be dangerous, lightning is the second most deadly is weather phenomena after flooding. Obviously, you can get struck directly by a lightning strike, um, although this is less common than other forms of electrocution. So, contact voltage is when you're touching something, maybe a handrail or something that is then struck by lightning. You get side flashes, which is when maybe a tree is hit, and if you're standing too close to the tree, then the lightning can jump halfway down the tree to you. Um, and that's also quite a common way to get struck by lightning. Um, Step voltage is also a common way for people to be injured. This is because the ground isn't conducting, and so when the lightning hits, you get a variation in electric potential with distance, so that between one of your legs and the other leg, you can have a difference in voltage, and then the current will flow up one leg and down the other. Um, this is more dangerous for animals because, if you go from the front legs to the hind legs of an animal, you're bypassing its heart. And so this is how a lot of livestock are killed. Um, there's also ground current, where you just happen to be in the path that the current is flowing as it's flowing in the ground. And lightning doesn't just come down from the cloud. You can initiate a lightning strike from the ground up, and then that includes from a person too. And here's the statistics of lightning injuries, just showing that direct lightning strikes, even though you would think that's the most dangerous, um, doesn't occur very often. Now, men are 9 times more likely to be hit by lightning than women, and I'll let you think about why that might be. Now, there's lots of advice that is given for if you're outside during a lightning storm, keeping your legs close together to reduce step voltage, making sure you're not close to trees, but also that you're not the largest object around either. These can all help, but really you just have to stay away from being outdoors during a lightning storm. Now, a lot of our understanding of how lightning occurs has really been revolutionized by high speed photography and being able to see how the lightning, especially in this video, sort of meanders around and then tries to find its way to the ground. Now, once it's found the path to the ground, that hot ionizing path is conducting, and all the charge from the cloud can travel along that path to the ground, and so you'll see um, the the lightning get very bright, um, and then it'll get dim, and this is because the charge, once it's flowing along the channel, um, other charge from neighboring regions is going to come in, and once it sees this hot ionizing conducting path, that can then flow along the channel too. And so you'll see it get brighter and dimmer and brighter and dimmer. And these are the different strokes within that lightning strike. And here's just another short video of lightning in slow motion. Now, the safest place to be is in a car, and this is because a car is made of conducting material. Now, inside a conductor, the electric field is zero, which means that if you're inside the conductor, you are shielded from the electric field and the current from the lightning strike. For example, this car that gets hit by lightning doesn't stop, and all the electronics are still working. This one seems to have a bit of a chunk taken out of it when it got hit by lightning. I'm not too sure if that's a piece of the road or what that is. Of course, cars are increasingly made from materials other than metal, and so it could be that cars are less conductive than they used to be. Um, Here's a car which seems to fare worse with lightning strike. Um, and I'm not too sure what all these people in black came from, but I suspect the damage might be because of the car's lack of a conducting frame. Now, we've talked a little bit about how lightning most commonly injures people, and how best to avoid it by being in a car inside. If you are outside, though, being the largest object is not a good idea. Also, having an arrow suddenly point to you in a video about lightning, also not a good sign. Athletes are also commonly susceptible to lightning injury, um, mainly when lightning strikes the ground and then travels out along the ground and causes multiple injuries to multiple people over a given area.
Well, unbelievable scenes here at the George Gold Stadium. Lightning is down, so is Shabani, and that bolt of lightning was straight down onto the pitch here. We could feel it in our commentary box, which shuddered. You can see the players holding their heads, Nanga as well. Surely they've got to call this off. If we can see it again. This was Lecheto. And there you can feel it, and look at everybody just collapsing.
Lightning can strike anywhere, and people have been hit by lightning while inside a house, either through the window or through a wall. There are lots of long-term effects from lightning strikes too. So the immediate effects might be burns, um, cardiac arrest and respiratory failure, things like that. But long-term effects are often ignored by the medical community. Things like memory deficits and mood disturbances and unexplainable fatigue. This person has a Lichtenberg figure, which is permanently now on his skin. Now, when I was younger, I remember they were talking about these transient luminescent events for the first time. These were phenomena that occur above the lightning that ordinarily we can't see from the ground. So people in the space station, when they were looking down at lightning strikes, they would see these red flashes going up, which are called sprites, and these blue jets and other phenomena. Of course, being dorks, we named them after Lord of the Rings things. So there's elves and all sorts. But we never knew that these existed. Now, one thing that's been reported for hundreds of years is a phenomenon called ball lightning. Now, to talk about ball lightning in a physics lecture is like talking about Bigfoot in zoology. It's always being considered a pseudoscience, and observations are incredibly rare. Now, some scientists claim that they've been able to observe ball lightning in nature, um, but this is very it's hard to reproduce because it's such a rare phenomenon. Um, Attempts to do this in the laboratory, though, have produced some effects which are very visually similar to ball lightning.
Oh, hells yeah. Keep rolling, baby.
I am. I see
Oh, it's
it.
time to the ball.
Oh, okay.
but it's not clear if there's any direct relation between what's occurring naturally and what occurs in the actual laboratory. That said, though, the fact that something can go from being a pseudoscience to potentially being part of the real scientific community is kind of exciting.